This talk today is going to cover a few different projects that I've been a part of over the years, and several of my collaborators are actually here in the audience. You can also talk to Sung Kim, Julia Plavnik, as well as Eric Rowell, Ching Zhang, and of course, Zhenghan Wang. All right. So since this is a summer school, I want to be pedagogical and start by trying to review some of what we've learned today, or rather synthesize it, and hopefully give you a sense of what it's like to do research in modular category theory, which Eric already gave a sense of in the previous talk, but maybe more so share some inspiration, and lastly, time permitting, tell you a bit about what I've been up to lately. So I want to go all the way back to fusion categories, which we started the morning with. And we didn't really talk about what it meant to have a strict fusion category, but starting with a fusion category, I want to say that there are, to oversimplify things a bit, two main tools that we use. One is to use the fact that every fusion category is equivalent to one that is strict. And what this means is that the associators, these isomorphisms that tell us how to translate between these left-associated fusion products and these right ones, are trivial. So this is a theorem of Maclane's, and it lets you, without loss of generality, trivialize the associators, which are the hardest part in many ways of working with a fusion category, which is sort of what a modular category is at its foundation. Another tool that we have is to use the fact that every fusion category is equivalent to one that we sometimes call skeletal. And you've seen this earlier today in Eric's talk and also yesterday in Dave's talk. And when you're working with a skeletal fusion category, what this means is that there's formally one object per isomorphism class of simple objects, let's say. And in particular, what this lets you do is pick a basis for all of your Hom spaces. And in particular, you can write down these things that you might have heard of called F symbols, which I'll review in just a moment. So two different ways to work with a fusion category, but it's not true that every fusion category is equivalent to one that is both strict and skeletal. One of the reasons why people love the toric code so much is that it maybe is one of these examples. The F symbols are all trivial, but in general, you can't have this. It's too good to be true. So to recap, there are sort of two main tools, at least for the purposes of this talk. One is passing to a strict category, which we might call strictification. And the other, passing to a skeletal category that's equivalent. And you'll hear people say skeletalization, skeletonization. They're all just made-up words, so it doesn't really matter. But you can't use both of these tools at once. And it's helpful to keep in mind when one of these tools might be more useful than the other. So to try to give you an idea of what the differences are, here's a little Venn diagram. If you've seen me give a talk, you know I love a good visual aid. What's kind of confusing about this subject when you're just starting out is that both of these ways of thinking about a fusion category have their own graphical calculus, and they're different. And you'll see them both in the literature, and it might confuse you. So I just want to recap a few things. I'll start on the strict side. When we, and some of what I'm writing down is slightly more general. So this, the diagrams that you'll see on the left here, these are called string diagrams. And these sort of predate the graphical calculus for modular tensor categories that will build off of these. But in this setting, we represent morphisms by these little boxes between strands. And what's going to be really annoying about my talk is that I'm going to sometimes use different conventions, whether I read diagrams from the top down or bottom up. I think it's safe to just read everything from the top down, but if you see something amiss, you may be right about that. But it shouldn't matter too much. So it's just a convention. But unfortunately, over the years, I've made different choices. So in this setting, when the associators are strict, then what we can do is write down tensor products of objects. So X, Y, and Z, these are just some arbitrary objects in your category. And I'm writing the picture that's drawn here is supposed to represent an associator. So you see at the top, these two are closer together, and at the bottom, these two are closer together. When the associators are strict, all these pictures are the same. And it doesn't matter. We're sort of able to freely group these strands. Okay. Now, when we're working with the skeletal fusion category, we work with graphs that are built out of trivalent vertices. And so we represent morphisms of this form, for example, with these trivalent vertices. And remember, let's say I'm reading from top down. I can think of this as, fuse A and B. Maybe I get the muth copy of C out of it. There will be mu many copies, or mu many basis elements in this Hom space. And once you've picked bases of your trivalent Hom spaces, you can pick a convention for how to write down bases of all of your Hom spaces. And you have things like the F moves, which tell you how to translate between pictures that look like this, local pictures look like this, and this. So I know it's a little bit small, but suffice it to say, these F symbols, you want to think about these as being the matrix entries of the associator. And they obey this relation in the graphical calculus. Now, in the overlap of this diagram is what these two graphical calculi have in common. So, namely, in particular, invariance. So something like fusion rules. So that makes sense no matter which one of these tools that you're working with. And I'll try to speed things up a little bit now. And to abstract things a bit, we'll be thinking about a modular category as a fusion category with some additional structure on it. We saw in Eric Raoul's talk that there are multiple routes to defining one of these categories, and I'm going to choose a specific route today. So similarly, in the strict setting, you would draw crossings like this, and that's probably not too shocking. In the skeletal setting, you have your R symbols. Again, these are matrix entries of your braiding isomorphisms. What's really cool is that pictures like this make sense in both of these diagrammatic formalisms, and they're invariants. And the physical interpretation when these categories are modular is that these are our little space-time diagrams of enions being generated from the vacuum, undergoing some exchange process, and then annihilating. So there's no ambiguity when somebody draws a picture like this, but you have to choose your tool. We heard that we can build a modular category by starting with a fusion category, adding a braiding. Of course, we want that braiding to be non-degenerate, but we also need something else. And this last addition to the diagram is maybe a little iffy. I think there's some, you could argue about what I've written over here on the right side. This might make sense over on the left side as well. But in either case, we draw pictures like this. we can talk about the twists of Enions in either one of these settings, and it makes perfectly good sense. But different diagrammatic formalisms depending on which way you're thinking about your category. Any questions before I move on from this slide? Okay. So when might you want to use one of these tools rather than the other? Well, if you want to do things like write down a Hamiltonian, compute some Braid or mapping class group representation, right? Figure out what kinds of quantum gates that you can build from braiding your Enions, or make some kind of protocol, then it's going to be really helpful to work with skeletal data or algebraic data, you'll sometimes hear it called. Briefly, the fusion rules, F symbols, and R symbols. Similarly, you can calculate, if you had all of this, you could calculate any framed link or three-manifold invariant that you wanted to, any Witten-Reshetikhin-Tarayev invariant associated to the category. You'll notice that I have fewer things on the left-hand side. That's not because there are less reasons to use strictification. We'll get there. But for those of you that have some experience working with Enion models, does anybody want to add anything on the right-hand side? So something you might want to do with this kind of data for physics reasons, say, or math? Anybody think of something that's missing? Okay. So strictification, on the other hand, it has some benefits. The diagrammatics are easier. It's arguably easier to prove more general results about modular category theory. Any mathematicians or physicists want to add anything to the left-hand side? Yeah.
Sorry, can I say something for
Please, go ahead.
I mean, this goes along with the background. You can calculate invariance, but it helps you distinguish between different phases of matter, different captures.
Yeah, and maybe invariants are of that flavor too. But yeah, okay. Anything else come to mind? Okay. If not, we'll leave it at that. So both of these have in common some graphical calculus. There's an asterisk there. It's kind of different. Yeah, you thought of something?
Not quite. I might be.
Question?
Yeah. So is there an analog? Is there like some finite data that's the analog of what you wrote in the bottom right corner in red that for the other side?
This?
Yeah.
So this is what you would call the skeletal data of a modular category, or if it doesn't satisfy the right properties, I guess a braided fusion category. And this is what you should think of as the data type of a modular category. If you're going to input it into a computer, then this is what you need. This over here is sort of manifestly not of a nature that you can plug into a computer. Yeah, not most of the time. Yeah. Any other questions? Okay. So these invariants in the middle, I just want to be really clear about what I mean when I say invariance. So these are quantities associated to our modular category that are preserved by symmetries, meaning equivalences of our modular category. So depending on whether you want to work really abstractly and categorically or really concretely and skeletally, you're going to think about these things in different ways. And so if you ask a mathematician, what does it mean to have two modular categories that are the same? They'll say something like this. There's a functor between these two categories that's an equivalence of the underlying categories, and it plays nicely with the monoidal structure, the tensor product structure, the braiding, and the twists, or the ribbon structure. And Dimitri mentioned this earlier as well. Something that's worth noticing here is that there's nothing explicit here about modularity baked into the notion that we have of what it means for two modular categories to be the same. It's just whether they're equivalent as underlying ribbon fusion categories. So non-degeneracy doesn't really enter into this story. Now, if you're a physicist, you might have seen something like this instead. Two Enion models, or let's say two skeletal modular categories, are the same if they're related by a gauge transformation. So there's some way to map certain states onto each other using unitary transformations in a consistent way, satisfying a couple of sort of obvious compatibility conditions. This is just where I pulled this from. I don't think it's the first place that it appeared. And when I wrote this down, I was kind of wondering, is this really the skeletal version of this definition, or is it missing something? And that's kind of a question for the audience. Are these two definitions really equivalent? Yeah. Because here, I mean, there's quite a lot going on. It's not a rhetorical question, by the way. These are the definitions. I haven't sat down and unpacked what this is, but exercise for one of you, or maybe me, okay? So depending on how you want to think about what a symmetry of a modular category is, what it means for them to both be the same, you can pick your preferred way of thinking about it and stick with it. But a warning, or maybe not a warning, but one of the goals of this talk, if I have time, for those of you that really love being over here, is to see some value in kind of working with tools that are manifestly categorical, right? You can do modular, you can work with Enion models without actually doing any category theory. Sometimes these are called 6J braided fusion systems. They're very combinatorial in nature. It's just kind of fancy linear algebra, right? But over here, maybe somehow we really need to take these definitions that we've been hearing all day seriously. So we'll see how successful I am at convincing you. It'll sort of depend. And so our favorite invariants of modular categories are the modular data, and we've seen them again and again over the past few days. And nobody ever writes the formula for the S matrix like this. They usually write it in terms of twists and quantum dimensions. And again, I apologize for not being able to zoom in. But these are just different ways to express the same thing. So if you're working, this is actually true in more general modular categories, not just strict, but just for the sake of today, we would talk about this as a trace of some morphism, namely this double braiding, and similarly with the twist. Whereas over here, we're going to be writing down formulas, maybe in terms of other invariants, but in terms of that data, the F symbols and R symbols, okay? But the pictures are unambiguous, and they represent the same thing. Yeah, so capital D is sometimes called the global quantum dimension, and it's the sum of the squares of the quantum dimensions of simple objects. So in pictures, maybe it looks something like this, where you're ranging over simple objects or isomorphism classes of simple objects, depending on how you're thinking about things. Yeah, so this is the same D that we've seen.
Maybe D squared.
Yeah, sometimes people, yeah, I always get confused about that. So
the circle is a square.
thank you. I'll just put a 2 there. Any other questions so far? Okay. We've seen that the modular data are highly, highly constrained. They come with this, they come forming this representation of the modular group, and so they satisfy some relations. They also have these nice number theoretic properties. And so there's a lot more you could say about modular data, but I don't have to because Eric did that for us. He also talked about classifying modular categories. And even though we've moved beyond unitary ring 4 modular categories, I always love to pull this figure from this earlier paper of theirs because it really solidifies this analogy that we love to talk about between classifying modular categories and building a periodic table for topological order. And sometimes it can feel kind of cute to talk about it that way, but I like to take that kind of seriously, as you'll see in this talk. So this is this table of up to rank 4, you know, it's in black and white. We start to see some, you know, similar patterns in the columns. These are all, you know, group-like cyclic group fusion rules. These are our quantum group modular categories coming from certain types of Lie algebras. And what I want you to compare this to is this very early version of the periodic table, which many chemists were thinking about, you know, up through the 1860s, and sort of compare it to what we just saw. It's very minimal. It's in black and white. It has hardly any information in it. Somebody who hasn't seen me give a version of this talk before, and since there are physicists in the audience, does anybody want to tell us what these numbers are? Do we see?
The atomic numbers.
Yeah, so if you look at something like carbon, which has 6 protons, I think its atomic number, we would maybe say 6, but it's atomic mass, right? These numbers? Yeah. So the number of protons plus the number of neutrons. Yeah? Okay. Now, this is from 1871. That's all the information that went into figuring out, well, not all the information, but right, it gives you a left to right sort of direction. It gives you rows. And then what breaks this into columns is like the similarities in the chemical properties, right? So which we sort of know has to do with the electron valence structure. Yeah. Is there something that's missing from this table? Sorry?
Isotopes.
Yeah. So this is from 1871. So does anyone know when they were discovered, roughly? How, like, if you had to get, like, it sort of surprised me when I thought about this carefully that we knew this much about the general structure of, you know, atomic elements before we even knew that if we looked inside the nucleus very carefully, there could be different number of neutrons there. But it wasn't until the 1910s, so some decades later. Yeah. Now this is the version of the periodic table, or a version that we like to look at today. It's very colorful. It has more information on it. This one, again, I can't zoom in, but it's got the valence structure, which, you know, maybe we sort of draw a very, very loose analogy to something like fusion rules, right? Some kind of numbers. It gives us some finer structure rather than just something like a single number, like a rank. But maybe this is some inspiration at how much more we'll know about topological order 20, 30, 40, 150 years from now. So,
but
yeah.
the table is fine, whereas,
That's how we tend to think about it, but it's sort of limited by, like, the conditions in our universe, right? If we sort of abstract, like, the mathematical structure, like the data that classifies each of these entries, right? You could imagine, you know, and surprisingly, I didn't know this until embarrassingly late in life, but there are still people whose job it is to, like, discover new elements and isotopes, nuclear isotopes. People still work on this, you know. They so something like appropriately this element named after Mendeleev. I think a new isotope was discovered last year. So people still chug away at this, even though practically speaking, it is finite. And I'll actually get back to that later. Yeah. So with this analogy, maybe bear with me a little bit. Different atoms can have the same number of protons, right? These are nuclear isotopes. They have different numbers of neutrons. And we've learned in the past few years that different Enion models can have the same modular data. And so you might call these things modular isotopes. So this is where the name comes from. All right. Now, this data here in this table, I'll explain a bit about now. But maybe first I want to be really careful about mathematically what I mean by a modular isotope. So we've talked about what it means for two modular categories to be the same. But if you have two that are definitely not the same, so if they're inequivalent, then we're going to call them modular isotopes if their modular data is equal up to relabeling. So what that means is, yeah, maybe we start out with different names for the topological charges, but we're just going to relabel them so that the things on one side appear on the other. So you might say their label sets are the same. They don't have to be ordered the same, so this is an equality of sets and not ordered sets, like we sometimes like to think about the label set as. And a modular isotope is going to happen if there's some way to map the modular data from one theory onto the other, right? So we're sort of thinking about fixing the Enion types, but permuting the Enion labels in such a way that once we apply that permutation, the two matrices, the S matrix and the T matrix, or the S matrix and the twist, they're actually equal on the nose, right? Any questions about this definition? Yeah.
What's the L over there?
Yeah. So oftentimes people like to use L as shorthand for what we call the label set, and this is just the set of different Enion types. So generally, it's a set of representatives of isomorphism classes of simple objects of a modular category. So for short, we might say something like L equals, the vacuum is always going to be in there, and then A, B. And we'll see an example in a minute. But any other questions? Yeah, go ahead.
So if these data are the same in two modular categories, what are the other gauge invariant data that can exist?
Yeah, so that's probably what the rest of the talk will be about. But if I haven't answered to your satisfaction, ask me again. Yeah, maybe we're just about there. Thank you. So first I want to start off with a non-example of modular isotopes. So let's take something like Ising or Ising, depending on if you want to pronounce it correctly or not. I don't know. Yeah, I know. I just peer pressure. So from the previous question, this is what we would call L for our Ising-like modular categories, right? We have our vacuum, our Ising Enion, I can't help myself, and our Majorana fermion, all right? So these are rank 3 modular categories, but there are actually 8 different ones. And if you take a look at their modular data, these 8 categories, they're parameterized by some parameter nu, and that parameter ranges from I think 1 to 8. Hopefully it's not 0 to 7, but if it is, somebody scream. The S matrix is the same for all of these, right? No dependence on nu. But the twist is different. So if somebody just handed you some set of modular data, you would be able to look at the twists and figure out which one of these 8 categories you had on your hand, okay? So these are not modular isotopes. They have different modular data, and there are 8 different ones. And at the risk of sort of confusing my punchline later, these things are related by a construction called zesting, which we've heard about at some length today already, but I'll talk about more later on in this talk. So here's an example, not modular isotopes, but related by zesting. Any questions about this? Yeah?
The different modular categories, the data is different. What physically, like, would you realize them in different systems, or what?
So I may not be the best person to answer that question, but the way I like to think about it is, you know, you're in future society where you're in a lab and you have some phase of matter realized, and you're in there, you're going to perform some experiment, and you do this sort of protocol that looks like this picture that we drew for the twists, something like this. You measure that, or by some other way that a real physicist can tell you, and you repeat the experiment until you can figure out which one it is. But these are gauge invariant quantities, so these are things one hopes you can measure. Yeah. Yeah. Go ahead.
Yeah, so you said these different categories are related by zesting,
Yeah.
and but I know that they're also related by stacking. So I guess that's the weight group composition or something. Does that mean there's a connection between those two things?
So there may very well be. I think zesting theory is still in its childhood, but there are lots of different constructions to realize the same thing, and maybe zesting's not the best way or your favorite way to think about it, but it is one way. Yeah. Okay. So time for these examples, and these are somewhat complicated and somewhat well understood. So they're a little paradoxical. I can only go into so much detail, but the modular isotopes that were first discovered by Mignard and Schallenberg, who are mathematicians, are of this form. So they're Drinfeld centers of fusion categories of this form, VecG, with the associativity constraint twisted by some cocycle. Now for these categories, there's a very specific group. This semi-direct product, these P's and Q's, they're odd primes. They satisfy some divisibility condition. This pins down what kind of third cohomology group you're looking at. It ends up being a cyclic group of order P. So it's bad. Notation's a bit of an eyesore, but something like this. So we've seen these today, but you might know or think about these things in another way. You might think of them as representation categories of these things called twisted quantum double Hopf algebras. You might think of these things as, realizing 2 plus 1D Digraph-Witten theory, TQFT. And you might also have seen them in the physics literature, just instead of rep of this thing, people like to write down something like d omega g. Okay. But I'm going to erase that. So these things have been studied by many, many people for a long time. And they're some of our best understood families of examples of modular categories. And yet, they have, while they're not exotic, they do have this sort of exotic phenomenon that occurs, which is that they realize modular isotopes. Now, there's some modular data on this slide, and all I want you to get out of this is that the parameterization of simple objects, which is by conjugacy classes, representatives of conjugacy classes of the group, and certain projective irreducible representations of centralizers. These are like very groupy things, right? In this modular data, these are characters of these representations. Everything inside is group theoretical. So this example, these are interesting examples, but they're also sort of classical in a way, just in the sense that everything comes from group theory, group cohomology, finite group representation theory. Now, if you want to really get your hands on one of these things, you can, yeah, go ahead.
I expect to have to rule out P equals 3, Q equals 7. But I don't think that's modular isotope.
So
P equals 3, Q
does
equals
P,
7.
yeah, that must be the case, because that would be smaller. So let me add this to save myself. Okay, thank you. Saving me from disaster. Yeah, no, that would have been nice if it were smaller. It would have made our lives easier. Because the smallest one of these modular isotopes is rank 49. So there are 49 types of enions in this theory, in this smallest example. So if I wanted to write down an S or a T matrix, I couldn't because it's going to be too big. Now I have it on my computer, but you know, this is an easier way for me to tell you what this modular data is than showing you like I could for the easing theories. But the way that you should think about this is that for this smallest example, there are 5 different modular categories, but if you look at their modular data, they cluster up. And in particular, if we sort of vary the choice of cocycle in the underlying fusion category that we're taking the center of, you know, let's call it category 1 and category 4, these have the same modular data up to a relabeling. And so if all somebody gave you was this, and that's all you knew, you wouldn't be able to tell me which one of these 2 things that you were looking at.
So this is the same group, the semi-direct product with different Ricard cycles, right?
Yes.
And so for each choice of a Ricard cycle, you get modular categories which are not equivalent but have the same modular data.
Yeah. Or so if the untwisted one has its own set of modular data. That one you can tell from the others, but otherwise they bunch up. There are 2 in this example per set of modular data.
So 3 sets of modular data.
3 sets, yeah. Okay.
Sorry, can you remind me where the cocycle goes into the structure of the category?
Yeah, so we start out with something that's just fusion. That's what this VEC G omega thing is, but the associativity is determined by some choice of cocycle. And then we take the center of that, and we learned today that's a way to cook up a braided category from a fusion category, and they happen to be modular. Right. So just a little comment on, you know, how did they figure this out? These things are huge. Well, they did a computer-assisted search and ruled out there existing anything of this form corresponding to groups of order less than 32. And what I've seen in a talk is slightly different than what's in the literature, but maybe 32 is also, maybe this is inclusive. And they can rule it out for certain higher groups, but their algorithm kind of slows down and it's hard to do. But anyways, they searched for these things. They searched for modular isotopes of this form, and they knew that it had to be really big. Yeah. Now, they had a theory that they used to convince themselves that these things were indeed in equivalent categories, but maybe it was sort of difficult for at least me to understand. So we wanted to understand these things maybe from a little more down-to-earth point of view. So back to the question that was asked earlier, like what are other gauge invariant quantities that we might use if modular data is not enough? Well, here's what you should know. If they have the same modular data, don't even bother, of course, trying to use the rank, because they'll be the same. The fusion rules, because we know from the Verlinde formula, those are determined by the S matrix. Things like central charge, higher Frobenius-Schur indicators, Gauss sums and higher Gauss sums, and we showed any link that can be realized as the closure of a 2-strand braid. So let me write this down. And you'll notice that my live handwriting is considerably worse than my pre-prepared handwriting. So in particular, so what you know is that something like this can't work. So you might ask, well, let me just throw more twists in the middle there and close it up, and will that work? And the answer is no, because that's something you can realize is the closure of a two-strand braid. So what this does is it just puts some lower bound on the sort of complexity of the link that you'll need if you want it to be a stronger invariant than the modular data. And this is not an exhaustive list, maybe, but lots of things that you might like, especially if you are a physicist, are no good for telling these things apart. So you have to do something else. And either you can appeal to some high-level construction that explains to you in a satisfactory way that these things are really different, or you find some invariant beyond modular data that can tell them apart. And that's what we tried to do. And so, maybe you're like, okay, what's the first thing I can think of beyond the S matrix? Maybe this thing called the punctured S matrix. Pictures like this, right? There's trivalent vertices in this picture. They're not gauge invariant. So things that you might like won't work either. But sort of motivated by this, we started thinking about something we called the W matrix, which is related to the Whitehead link. It comes from a certain framing of the Whitehead link, which I like to draw in this way, because I think it's prettier than the way I used to draw it. But this quantity, it's an invariant. You can just tell by looking at this picture. And it's determined by invariants we already know and love, like the S matrix, twists, and the punctured S matrix. So in some sense, this is maybe like the next best thing to a punctured S matrix. Yeah. Sure.
How do you lose gauge invariance by puncturing an S matrix?
So remember, when we looked at the definition of a gauge transformation earlier, we have a degree of freedom where we can multiply any trivalent vertex by a unitary, and so we can always mess that up. Yeah. So no trivalent vertices allowed. So, yeah. Mm-hmm.
Why is the W link not two-strand link?
Yeah. Maybe. So the minimum braid word in both width and length that you can use to represent the Whitehead link is this. And this is, sorry, this notation's not very clear. I haven't explained it yet. But it does require the three-strand braid group. Maybe you were thinking to like turn this picture on its side or something. But yeah, this one can't be realized as the closure of a two-strand braid. I don't have a better answer right this moment for why not. I guess we'd have to kind of stare at it and convince ourselves.
It would be pretty easy. This is how the thinking member is zero. So I have two-strand is always
Well, that's a great answer. Thank you. Yeah. What I needed was more invariance. Okay. So we were interested in the W matrix because maybe it's like the next thing you might think of. But with Alan Tran, who's now at HRL, we used partial algebraic data for this rank 49 category, right, which is huge. We didn't have full algebraic data. We did not have the F symbols for a rank 49 category, but we had enough to calculate invariance of small knots and links. And I'll say more about what I mean by that in a moment. But we wrote some code to compute some more invariance, and we systematically checked whether they could tell the difference between these modular isotopes either with or without the modular data. Okay? And so I went to these tables real quick, but we churned out a bunch of data. And this is notation that topologists use to enumerate knots and links in terms of increasing complexity. The second column is a minimum braid word representing that link. And this notation, I'll probably get some conventions wrong, but A is something like, let's say, sigma 1. B is something like sigma 2 in the usual braid group notation, and the lowercase are their inverses. And I almost certainly got the convention wrong, but I think I got it right in at least one of my papers. So we asked whether they sort of distinguish these things weakly or strongly, which just meant either with the help of the modular data, so ST plus whatever you're looking at, or strongly, by which we meant it's a complete invariant on its own. Forget about S and T. If you just compute this one invariant, you're golden. Yeah?
So, okay, so these are called two-component links. And before you said that this discussion just now, that the other thing wasn't too closed something?
Yeah. So if we have a link that can be represented as the closure of a two-strand braid, what that means is I can draw some element of the two-strand braid group, and after I sort of move crossings around and I close it up, it always looks something like this, where there's some number of crossings in the middle. So this is the closure of a two-strand braid, and this can either be one or two components. But if you have something that's two components, it's not necessarily of this form. So the two is different. Yeah. Yeah. Thanks for the question. So this is another picture of the Whitehead link, and it appears here. So again, it's one of the very first things that you would find when you're doing this systematic search. Okay, but lots of things have this property, and so you might ask the question like, what makes these good invariants? This is just raw data. It's hard to interpret. Why, is the W matrix actually a good invariant or not? Are these better? And so, again, I should be careful here. This qualification was, what I mean by small knots and links was representable as three-strand closures. So traces of things in the three-strand braid group. We did some for four, like the Borromean rings, maybe. But the runtime of our algorithm got really long, and so yeah. And also, partial algebraic data was very constraining. Like, we were lucky that we could compute this. And we did this for knots, too. You might think, well, the S matrix wasn't good enough. Like, definitely you'll need two components, but maybe it's a little less common. But again, one of the very first things you would look for, something like this is the 5-2 knot, is a complete invariant for these categories. And here's some other thing, some non-alternating knot with 8 crossings, and it's the 21st thing that appears in some enumeration. So kind of mysterious, but we had this data. So that's how to detect modular isotopes, but how do we explain them, at least in a way we could understand, because this is experimental math, or maybe physics. Depends who you're asking, right? But we want a theory that explains this. And so what we'd like to be able to do is appeal to some construction that explains this. And I'm telling this story like this happened seamlessly, but some number of years later, after this construction called Zesting came onto the scene, we realized that these modular isotopes could be realized through Zesting. And so this was a new way to think about these modular isotopes that we didn't have before. And this is work together with Sung Kim and Julia Plavnik. And I mentioned both of these people are here if you want to chat with them about this. And maybe in the interest of time, I don't want to say, I don't want to get too bogged down in detail about ribbon zesting, but the idea of the construction is that we start with our category, and this is a very general construction, but let's just think about modular categories for today. We choose some grading, and it's going to be necessarily abelian because our category is braided. We choose some grading of our category. We've seen that definition a couple times today. It means that if we take something in the A-graded component and tensor with something in the B-graded component, let me write this down properly, then we get something in the A-B graded component. And I am going to use multiplicative notation for A, even though it's an abelian group. So sorry. Okay, So this is in C, A, B. Okay. So when I write this, I think this is an important point to clarify here. So now I'm using different notation for my objects. X sub A means I have an object X, and it lives in the A graded component. So before I was using like lowercase a, b, c, things like that, as Enion types, but I've switched notation, forget all that. These are objects, and now lowercase Latin letters are elements of a grading group, okay? So we pick some grading, and then we mess up the fusion rules. So we have an old fusion rule, but we define a new one where we take the old tensor product and we tensor with an invertible. And ring theory will tell you that you can't just pick any invertible that you want to mess up the fusion rule. This needs to be a 2 cocycle valued in invertibles. So this is a 2 cocycle lambda. And in order to make sense of this construction and write this down sort of without too much confusion, we're going to assume that we're working with a strict modular category, right? So all of that data I showed you, that was all skeletal. That was using partial algebraic data. That was R's and F's. And now I want to forget all that, and I'm just going to take those modular isotopes, and I'm going to assume that they're strict, okay? So that I can apply zesting. Now, we saw some explanation of zesting earlier, but I want to explain it in terms of pictures, right? But the whole point of strictification is that the graphical calculus is easier. And in this setting, where we're thinking of a modular category as having, you know, a fusion structure, a braiding, and some ribbon twists, we can track how messing up the fusion rule propagates through those layers of structure. And what happens is that we have degrees of freedom to play around with each of these layers of structure. And so whereas before our associators were boring, they were trivialized, now they're going to be non-trivial. So now the zesting is not going to be strict anymore. It's also not going to be skeletal necessarily. And this is a picture of my new associator. And because I'm running a little low on time, maybe I won't say too much about these pictures except for you can think about zesting completely diagrammatically. Now, not in terms of the diagrams that have F moves and R moves, although you could do that as well. But for now, what happens to these kinds of local pictures, okay? This is work with Julia, Eric, and Ching, who are all here, and you can chat with them about this. So there's some new pictures we can draw in our new zested category. And because a lot of tears were shed over these diagrams that I've typed up, I'm going to break the aesthetic of my talk so far and put these in here. So we can think about zesting completely in terms of data and diagrams, which maybe if you're into physics, that's okay. Like, it's okay not to have algebraic data. Maybe this is good enough. So in the zesting construction, and this is a little bit of an oversimplification, we have some choices we can make at each stage. So some 2 cocycle that we change the fusion rules by. We zest the fusion rules. We choose a way to zest the associativity. We can't just make any choice. We want to get a fusion category out. And if you look at what the pentagon axioms look like for these zested associators, what will pop out is this thing you might call the associative zesting condition. And similarly, if you sort of go through this machinery, you'll see, what needs to happen in order to end up with a braided category. What needs to happen in order to end up with a ribbon category? I want well-defined twists. I want well-defined trace. I want all of the nice things. Ideally, we're all here for one thing, modular categories. We want to get something modular at the end. And these pictures are a lot. So again, all I want you to get out of it is there's some way to think about this construction in terms of some data, so some 2 co-cycles. This lambda we saw earlier is a 3 cochain, some isomorphism, some function, satisfying some picture relations. And we like that kind of thing. Okay, so this is what a zesting is at a glance. And this is very closely related to a lot of existing constructions. So it's closely related to G extension theory. It's closely related to work that Dave has done, and you can ask him more about this. It's sort of maybe a more skeletal way to think about zesting and extension theory in this very like data-driven way. And Dimitri has a theory that I think is more general than what we mean when we talk about braided zesting, but I think some braided zestings can be interpreted as deformations of some braided monoidal 2 functor, so there's some higher way, some more enlightened way to think about this, which I won't pretend to understand yet. All right, so I just wanted to mention that. So what's nice about zesting is that it's really easy to say what happens to the modular data. And this is, I say easy, but maybe that first formula looks kind of scary. But what you see happening is that you have a new, you choose some data, you're going to zest your modular data, and it's going to be related to the old modular data by some scalar factors, by some phases that only depend on the zesting data and the grading group that you chose, the gradings of simple objects. There's a particularly nice version of this theory where the formulas are much simpler, and it looks something like this, which you'll vastly prefer. And I might be getting one of the signs wrong here. So let me get this right. This is a lowercase s. Okay. So in this special case of something we call cyclic Tanakian zesting, which I won't get into, it's just a very nice special case. The modular data transforms in a very nice way. And in particular, it can be parameterized by a single variable, which is this lowercase s. And it's possible that I messed up the signs. I got them swapped on these, but I can check that later. Okay, so easy to compute what happens to modular data under zesting. I will skip talking to you about how we proved that these modular isotopes come from zesting. And maybe finish by sort of going back to this question about, like, isn't the periodic table finite? People really do work on still finding new isotopes, nuclear isotopes, but they're synthetic, so they don't actually occur. Maybe these rank 49 things that we've studied, no one's ever gonna really care about for physics reasons, but they come from zesting, so we have a theory to explain them. And maybe they are sort of not important to our understanding of the structure theory of modular categories, but they do exist, and we need to keep it in mind. If you're just working with modular data, it's not clear whether there are multiple modular categories being represented. And I think the last thing I want to say, so zesting helps explain modular isotopes, but it also helps explain their topological invariance. So if you look back to that table of data that I had, it was, I guess, informative, but in a limited way. It turns out that just like we could say what happens to S and T, it's very straightforward to pick a link and zest it. So we saw how to zest associators and crossings, and we can zest cups and caps, or we can zest twists. We can zest link diagrams. And if you do this, what you find is that under zesting, these invariants, these quantities transform in the following way. They decouple into two pieces, one of which is the original invariant. So the thing that you started with, your original S, your original T, in this case, your original Whitehead link. And then a piece that depends only on zesting data and the gradings. And there's nothing special about S or T or W. This is a general phenomenon, and so we have a theorem that if you look at these Witten, Reshetik, and Turaev invariants under zesting, they always transform in this way. The invariant is going to transform graded block by graded block in a way that only depends on zesting data. So the simplest thing I can say is, zested invariants decouple, maybe, to keep it short. And the proof is just a diagram, basically. But this helps us get a little better understanding of what's going on with these invariants. Rather than just computing them, now we have a theory that sort of explains them, at least relatively. So my subtitle for this talk was The Science of Enion Models. We ran some experiments. We made a bunch of data. We didn't know what the heck was going on, but we tried to think about it. We, didn't know. This didn't directly lead to the theory that we developed, but then a theory came along, and we sort of explained these modular isotopes, at least a little better. It's one way to think about them. And here I am telling you about it. So science, it works. And some follow-up questions, Eric touched on these earlier. Okay, do all modular isotopes come from zesting and maybe braid reversal or some other really simple thing that we're not worried about throwing in the mix? Can we use zesting to produce smaller modular isotopes? The smallest known ones are rank 49. Maybe we can push that way down by using zesting. So S and T aren't complete invariants for modular categories. This theory helps us, I believe it will help us get a better handle on what are good invariants to use to study modular isotopes, but the theory of zesting is still kind of young. But once we sort of understand it a little better, I think we'll be able to say things like, well, we really like this invariant, like the W matrix, because what ends up happening is that some of this, like this diagram on the right, actually contributes something. The invariant sort of depends on the zesting. It maybe detects the zesting, you might say. And so maybe that's what makes this a good invariant for studying these things. But it's subtle, and there's still more to do. So sorry for going a little over, and I'll stop there.